Marginal analysis. In this section, we're going to connect what we've learned about derivatives and the instantaneous rate of change to what we learned about cost and revenue and profit in a previous section. We're going to be asking what happens to these economic functions on the margin. So what does marginal mean? So when we're talking about marginal analysis, we're talking about the impact of adding one more unit of whatever it is that we're making. So if we're talking about marginal cost, which we're going to denote C prime of Q, like you can see here, is the additional cost to produce one more item. And we can estimate this by looking at the difference between the cost at one level and the cost at that level plus one. So this additional cost to make this item is called the marginal cost. So we're going to use the words marginal cost and the notation C prime of Q interchangeably. Similarly, marginal revenue, which we're going to notate as R prime of Q, is the additional revenue from selling one more item. And we can again estimate this by looking at the revenue at one level and the difference between that and if we were to sell one more. Marginal profit is the additional profit from making and selling one more item, and we can approximate this by looking at the difference between the marginal revenue and the marginal cost. So let's look at the cost and revenue functions a little more closely to see how we can extend what we've already learned. So for cost functions, again, we're going to use C of Q, where Q is quantity and cost is in dollars. We've been assuming to this point that cost is linear, where we had a fixed cost and a variable cost. And so if cost is linear, then the marginal cost is going to be the slope of the line, which is the same at every single point. So it doesn't matter what quantity we choose. In order to add one more, it's always going to be the slope of that line. However, there are certainly a lot of instances where your cost is not linear for whatever reason. And so now we can extend this to other types of cost functions. So if your cost function is not linear, like in our example over here, then the marginal cost is going to be the slope of the tangent line at the point being evaluated. So what does that mean? That means we can't just assume one marginal cost for every single point. We need to pick a specific quantity and then evaluate the tangent line at that point. So for example, if we were going to pick this point here, in order to get the marginal cost, we would come up to the graph at that point and approximate the tangent line at that point, which might be different if we picked our Q star to be somewhere else. So marginal cost, which is the slope of this tangent line, is going to approximate the additional cost to move one unit away from the point we're looking at. We can look at revenue in a similar fashion. So again, up until this point, we've been looking at revenues that are linear. We've been assuming that our revenue is generated by doing price times quantity. If we have a revenue that's linear, then the marginal revenue, again, is just the slope of the line at every single point. So the marginal revenue is the same everywhere. However, if the revenue is not linear, because maybe there's some sort of depreciation if someone's buying in bulk, you're going to give them some sort of discount so you don't take in as much, or something of that sort, then again, we're going to approximate the marginal revenue by picking one point that we're interested in finding the marginal revenue, and then we're going to approximate the slope of the tangent line at that point. So again, we can now extend to look at some revenue models that are not linear because now we can approximate how the things are changing. So let's go ahead and look at some examples of how we could evaluate various economic applications. Example 1. Suppose that the revenue for a certain item is given in the table below. Determine the marginal revenue at Q equals 15. So here, if you look at our rows, Q is in the top row. It is our independent variable. And revenue is in the second row, which represents our dependent variable. We're interested in what's happening when Q equals 15. Now, this is a little bit different than how we've approximated derivatives in the past. In the past, when we were evaluating a derivative, we would check the rate of change to the left and the rate of change to the right. Sometimes we would average those together. But remember, our definition of marginal revenue, cost, and profit always talked about what would happen if we added one more. So we're always thinking about the right-hand approximation because we're asking what happens if we move one unit ahead. And we do this because in business, we're not really concerned about what's happening to the left because that stuff has already happened. So here, we want to approximate what's going to happen if our revenue goes from 15 to 16, right? But we don't have 16 on this table, which is why we're going to approximate the marginal revenue by using the point to the right that is closest to 15. So we're going to look at the rate of change between 15 and 20. So in order to do that, we're going to do the change in R over the change in Q. So we're going to do 180 minus 160. So those are the two dependent values over 20 minus 15. So on the top, 180 minus 160, I get 20. And on the bottom, I get 5. So when I crunch that number, I get 4. So how do I talk about this number 4 and what does it mean? Okay, well, I'm approximating the derivative of revenue at 15. And I can't really say equals, so I'm going to make this a squiggly line. I'm approximating my derivative. And this is going to be $4 per item. Okay, so quantity, Q, I don't know what I'm selling, so I'm just going to call it item. And the marginal revenue being $4 per item means that for each additional item that I sell, I am expecting to get 4 additional dollars. So to go from 15 to 20 is 5 additional items. 5 times 4 is 20, so I go from 160 to 180 in terms of my revenue. So if I was going to try to approximate how much revenue I would have at 16, right, R of 16, I could add $4 to the 160 because for every increase of 1 in quantity, I'm expecting my revenue to increase by $4. So that's what it means at $4 per item. Let's look at another example. Example 2. Suppose the cost of a particular item is given in the graph below. Approximate the marginal cost at Q equals 10. That's part A. So let's do that first. So here I have a graph. So I'm interested in what's happening when Q equals 10. So I go to 10 and I go up to my graph and I draw in my point. Now I notice something really interesting here that I think will be really helpful. I notice that my cost equation is linear. Okay, and I know from before that if my cost equation is linear, that my marginal cost is the slope of the line. So I'm looking to find the slope of this line. If this was not linear, I would need to draw in a tangent line and find the slope of that. But here it is linear. So I notice that when Q equals 10, my cost is right between 100 and 200. So the cost is 150 is the dependent value. So now, in order to find the slope of this line, I need another point on this line. And I can pick any other point on this line. So I'm going to try to be strategic about where it lands. So I'm going to actually pick this point right up here in the corner because that has pretty nice values. So when Q equals 30, that's my Q value, my cost is $300. So that's another point on this line. So to get the slope of this line, I'm going to do the change in y over change in x, which is the change in the dependent values over the change in the independent values. So I have 300 minus 150 divided by 30 minus 10. And that gives me 150 over 20, which when I crunch that as a number is 7.5. Now, I need to think about what this number means in order to interpret it. So remember, I was trying to figure out the marginal cost at 10. So I'm saying C prime of 10 equals 7.5. But remember, this has to do with money. So I'm going to throw on the 0 after the 5 because we're actually talking about $7.50. But it's not just $7.50 because I'm talking about the derivative here, right? So the top value when I did my change in Y was cost in dollars, but on the bottom, my change in X was the change in items. So it's $7.50 per item. So what that tells me is that for each additional item that I make in order to sell, it's going to cost me an additional $7.50. My cost will go up by that amount for each additional item. So if I know the cost to make 10 items, which was $150, if I wanted to make 11 items, so one more, it would cost me another $7.50, so it would be $157.50. So I can then use that to figure out my cost for any quantity. Here, because I'm not approximating, I have a line here, so the slope is going to be the same, I can use the equal sign. Part B says if R prime of 10, so the marginal revenue is $15, so I'll get an additional $15 if I go from selling 10 items to 11 items to sell one more. Then what is the marginal profit for this item? So what we need to do here is we need to remember that marginal profit at 10 items, which is the additional profit from making and selling my items, is going to be marginal revenue minus marginal cost at that level. So R prime of 10 minus C prime of 10 is going to be what? Well, R prime of 10 was what was given in the problem, so that's 15, minus C prime of 10. Well, that's what I just solved for, right, up here. So minus 750, 15 minus 750 is $7.50. So if I were to make and sell one additional item, moving from 10 items to 11 items, I can expect an additional $7.50 added to my profit, my marginal profit. Okay, let's look at another. Example 3. Consider the graph below and determine when this product is making a profit. So the question itself we can answer visually, but there's a lot of other important information we can get from this picture. So let's start by remembering when we are making a profit. We need our revenue, the amount of money we take in, to be greater than our cost. So if the money that we're taking in is more than the money that we're putting out, then we're making a profit. So if we look at our picture here, revenue is this linear function and cost is the wavy function. So the area where revenue is greater than cost is this area between 130 to 215. If we wanted to use our interval notation, we would use open brackets because at 130 and at 215 is when they are equal and therefore would be 0. So that's the interval where we're making a profit. But here we've been talking about marginal analysis. So I want to point out a couple things. So this is the area where we want to be as business people. We want to be between 130 and 215. How do we decide if we want to keep making more? Okay, so the optimal place for us as business people is where the difference between revenue and cost is the largest. So somewhere right here. This is where we want to optimize our production because that's where we're making the most profit, where the revenue and the cost have the largest difference. If you look at the points before that, you will notice that marginal revenue is greater than marginal cost. Okay, so marginal revenue, the slope of that line is steeper than marginal cost. When that's true, you want to keep producing more. When your marginal revenue is greater than marginal cost, that means your marginal profit is positive. So you keep marching closer and closer. Once you get past that optimal point, look at what happens. Okay, so here, when we are past this point, the marginal cost is greater than the marginal revenue. It's steeper, which tells me that my marginal profit will be negative because I've moved past the optimal point. So by comparing your marginal revenue and marginal cost to see which one is larger, that will give you some insight into whether or not you should keep making and selling more. Whenever marginal revenue is greater than marginal cost, you should keep producing more. If marginal revenue is less than marginal cost, you should produce less. And as you may have guessed, at the exact point where we are optimized, where we have the greatest profit, is the exact point where marginal revenue is equal to marginal cost, right? That's the point we're always aiming towards. So even though we were able to answer this question pretty straightforward about where the profit is positive, there's also a lot to be learned from looking at the picture about how we make decisions to optimize our profit. Let's look at one more example. Example 4. Let's see if Q represents the total cost of producing Q items. Suppose that C of 15 equals 2,600 and C prime of 15 equals 109. Estimate the total cost of producing the following number of items. A, 20 items, B, 10 items. So for part A, we are looking to approximate C of 20. We want to know the cost of producing 20 items. Since we have information about the function at 15 and the derivative at 15, we can use local linear approximation to try to get a pretty good estimate of the cost at another point. So here, using local linear approximation, we're going to say the cost to produce 20 is the cost to produce 15 plus the marginal cost, so how much that's changing at 15, times 20 minus 15. So this is how far away we are trying to approximate, 5 units, right? We're going from 15 to 20, so that's 5 units in the future. So we're going to multiply that 5 by the rate at which we are changing, and we're going to add that to our starting point. So we have 2,600 plus 109 times 5. 109 times 5 is 545. If we add those together, we get that this is approximately $3,145. So here, our cost to produce 20 is more than our cost to produce 15, which makes sense. Similarly, if we want to approximate the cost to produce 10 items, we again have information about what's happening at 15. So we're going to use the cost to produce 15 items plus the rate at which we are changing, the marginal cost. And now we're going to do 10 minus 15. So you always are going to do the point you're interested in minus the point you have. And the reason we do that is that here you'll notice that that's going to give us a -5, which is important because we're talking about what happened at an earlier point in time. The information we have is about what's happening at 15, but we wanted to know what was happening back at 10. Maybe for some reason we don't have that information, so we actually have to move in a right to left situation, which is not usually the way we're doing things. So again, we're going to fill in what we know, 2,600 plus 109 times -5. So 109 times -5 is -545. So if we add those together, we get that that is approximately $2,055. Now this makes sense because the cost to produce 10 should be less than the cost to produce 15, which we are able to get to because of this factor here.